So here are a few notes on related rates, and just an example to take a look at. We know the area of a circle just depends on the radius. So let's say we evaluated some different radii. So when the radius of a circle is 1, the area is pi r squared. So it's just going to be 3.14 pi because 1 squared is 1, so pi. And then I calculated these out. When the radius is 2, the area is about 12.57. So if you just put the 2 in there, 4 pi is about this. 9 pi, 16 pi, 25 pi, so pi r squared. We just square this and multiply times pi, so we got these values for the area. And if this radius was changing every second, it was moving up 1, so after 1 second it's 1, after 2 seconds 2, 3 seconds the radius is 3. Notice that the rate of change of the radius per second is going to be 1 unit per second, but the rate of change of the area is going from 9 to 16 to 22 to 25. It's changing faster. So you see these two rates, rate of changes of the radius and the rate of change of the area, they are related by this formula. So sometimes that's what we can think of as a related rate situation. So most related rate problems, now notice this is just from my observations, most related rate problems use geometric figures to provide the structure of the relationship of the data given in the question. And we call that modeling. So I'll give you an example. Example, one car is traveling north at 50 miles per hour. Second car is traveling east at 60 miles per hour. How fast is the distance between them changing after 4 hours? So if we just draw a sketch, again we're going to use a geometric figure to relate our data. Now this is the car moving north, and since we usually use the vertical coordinate y, we'll call that y as a function of time. This other car is moving east, so we call this x as a function of time. And the distance between them, you notice as they are moving, this distance is going to be getting greater and greater. And that's also going to be changing as a function of time, and we'll call that h. Well, now we're using right triangles. So that's how we're going to relate our data. So we know that y squared plus x squared equals h squared, and we'll go on from there as we do some of these problems. But you see, we're just saying, I just wanted to show you that we're using a geometric figure, okay, to model or structure our data so we can see our data is related by this geometric figure. So obviously you're going to have to go back and review some of the geometry formulas that you learned, because these are all going to be coming into play, or a lot of them will be coming into play in various problems. So I kind of went over some of them here, or I'll go over some of them, excuse me. So these are what I call things we need to know, or some useful formulas. Here we go. Now if I'm going too fast, you can always just pause it and write these things down, think about them. So that's a nice thing about having a video. You can always pause it, think about it. So these are things we need to know, or some useful formulas. First one is pi. Where does pi come from? I think I've talked about this before. Pi comes from the circumference of a circle divided by the diameter. If you take any circle and you measure the circumference and you divide it by the diameter, which is the chord that goes straight through the center, you'll get pi. So this is one of our basic geometric, this is our basic geometric formula for circles. And then we can multiply both sides by d, so this would imply that circumference equals pi times diameter. But we know that the diameter is 2 radii, so I can say circumference equals pi times 2 radii, or 2 pi r. So this is how I remember the circumference equals 2 pi r formula. And then we know the area of a circle is pi r squared. That's a given formula. So this is for a circle. Then we'll also be dealing with spheres. Okay, a sphere is a ball. Or if we take a circle and rotate it around the axis, we'll get this sphere. And the volume of a sphere is 4/3 pi r cubed. And the surface area of a sphere, that means if we wanted to paint it or cover it with some type of material, we need the surface area. That's going to be 4 pi r squared, or 4 areas. So we'll be using these formulas. Also right triangles, a lot of right triangles. You just saw one using the cars. Moving north and east. So right triangle, we know that if we have a right triangle, we know that a squared plus b squared equals c squared from the Pythagorean theorem. So I just label these y, because y is usually the vertical axis and x is the horizontal axis. And we could call the hypotenuse h, we can call it r, we can call it s, we can call it whatever we need to. We usually don't call it d because we're taking derivatives and we have d dx dt or dy dt, so we have d dt, it's a lot of d, so usually we'll avoid that. Okay, but in this case, x squared plus y squared equals h squared, so there's our Pythagorean relationship. And then from the Pythagorean theorem, we can derive the distance formula. If we have two coordinates, or 2 points, and we have their coordinates, x1, y1, x2, y2, we know the distance between those 2 points is given by the square root of x2 minus x1 squared plus y2 minus y1 squared, and this is a direct result of the Pythagorean theorem. And then if one of our points is 0, let's say our x1 is 0, so we're talking about the distance from the origin, then from the origin that distance would be the square root of x squared plus y squared. So that's a handy formula also. And again, I'm going through these fast, so you can always, again, pause and think about it. Okay, triangles, area of triangles, and we know our basic area of a triangle is 1/2 base times height. Sometimes we have to find the area of an equilateral triangle, and we're just given the side. So how do we do such a thing? So I usually like to derive that for my students because we derive it in geometry, but sometimes we forget that. So we know the area of a triangle is 1/2 base times height. That's our basic formula. So, and we all remember that, but we all usually don't remember this one. The area of a equilateral triangle is the square root of 3/4 times side squared. So how do we get this? Well, we have an equilateral triangle, and we know all the sides will be the same, and all the angles are 60 degrees. So if we draw the altitude, we know that's going to be a right angle, so it's going to form two right triangles. And both these right triangles are going to be congruent by a number of ways. We could say hypotenuse leg, or we could say angle, angle, side. But these two triangles are going to be congruent. So if these two triangles are congruent, these two sides are congruent. So if this whole side is s, this side would be s over 2. So we know that h, s over 2, and s are the sides of a right triangle, so we can find out what h is. Oops. I think I meant to color code these, so I call this h here, h squared. So we know that h squared plus s over 2 squared equals s squared from the Pythagorean theorem, and we can solve for h. So this is going to be s squared over 4 plus h squared equals s squared. And then if I subtract 1/4 s squared from 4/4 s squared, because that's the same thing as 1 s squared, I get 3/4 s squared. And then if I take the square root of both sides, h equals the square root of 3, and the square root of 4 is 2, and the square root of s squared is s. Now it's usually the absolute value of s, but s is going to be a distance, so it's always going to be positive, so we don't worry about the absolute value, because s will always be positive. So we can put this back in our formula. So area equals 1/2 base, and the base is s. The whole thing is s. And the height is the square root of 3/2s, and then if we just simplify this, we get square root of 3/4, and s times s is s squared. So there's your area of an equilateral triangle if you are given just the side. Another formula that comes in handy is the area of a triangle, given two sides and the angle between those. And this is another one that's easy to derive. If this is a triangle and we know one side, the angle, and the other side, or the two sides and the angle between them, okay, if we want to find the area of this triangle, again, we're going to go back to our basic formula. Area equals 1/2 base times height. But by using this right triangle, I know that the sine of theta is the opposite side over the hypotenuse. So the sine of theta would be h, my height of my triangle, over a. I can multiply both sides by a, so h equals a times the sine of theta. And then I can just substitute in this h into the basic area formula. So area equals 1/2 base times a sine of theta. And then we could just put the a in front using the commutative property of multiplication. And area equals 1/2 ab times sine of theta. So area of a triangle is 1/2 the product of the two sides times the sine of the angle that's between them. So that's another handy formula. And we'll do some more in just a moment.